Hello. I would like to thank Professor Valerie King for visiting us from the University of Victoria today. Her research interests involve randomized algorithms and data structures. Most recently, she's interested in distributed computing, and today she will talk about consensus problems, how to elect leaders and in a malicious environment. This is her recent work from Stock, POTC, and other top conferences. And with that, Valerie, please.
I guess oh, it's on.
Yes.
Great. Hi, it's really a pleasure, really interesting to be here, I have to say, and the lunch is great. And thanks for coming. Okay, so it happens to be the silver anniversary of the Byzantine Agreement problem. And as I came to this area relatively recently, I'm gearing this talk to someone like me who doesn't know very much about distributed computing. So if you don't know much about the topic, that's fine. I'll try to sort of catch you up a little bit. So it's the silver anniversary of this problem. And here's a famous quote that sort of started it all. We imagine that several divisions of the Byzantine army, can you hear me all right? Oh. Several divisions of the Byzantine army are camped outside an enemy city, each division commanded by its own general. The generals can communicate with one another only by messenger. After observing the enemy, they must decide on a common plan of action. However, some of the generals may be traitors, trying to prevent the loyal generals from reaching agreement. Now, strangely enough, I read that it wasn't originally the Byzantine Agreement problem, it was the Albanian Agreement problem, but they decided that there were real people, still people living in Albania, so they didn't want to offend anyone, so they changed it to the Byzantine Agreement. So there's nothing important about the word Byzantine. Then it doesn't have to be complicated. And that's Leslie Lamport. I was working at Microsoft. A few blocks away from here, Leslie Lamport is in the Microsoft Research Lab where I was. So I put his picture up. So each processor starts with a bit. And the goal is that at the end of the protocol, there'll be some protocol. And at the end of the protocol, each processor must output a bit, the same bit. And that bit has to agree with at least one of the input bits that one of the good processors had. And now we also assume that there are corrupted processors. T is always going to stand for the number of bad processors. And they're controlled by a malicious adversary, meaning that the adversary can control all of the processors at the same time, and they share information. And it's like having a single centralized mind controlling the actions of the corrupted processors. And resiliency is the word they mean it's the T that the protocol can tolerate and still succeed. So it's the number of bad processors that the protocol can tolerate. And it also happens to be the year 2007, the year that Nancy Lynch wins the Knuth Prize for her work on this problem. So 2 years after the problem was posed, Nancy Lynch and Fisher and Patterson showed that even if there is one faulty processor, it's impossible to have a Byzantine agreement in the asynchronous model if you have no randomization, if it's a deterministic. So in other words, a deterministic protocol is impossible for this problem. And her result is celebrated, and I put that in quotes because every time someone refers to this result, they always call it the celebrated result. So it's the celebrated result, and it is fundamental in all of computer science, so they say. And it launched a whole field. I mean, the whole field of distributed computing came from this, I think. Okay. Okay, so Google Scholar turned up 1,200 sites to this paper, or to Byzantine Agreement, and probably it's more by now. And there are millions of, many problems, models in which this problem has been addressed. And it's really You know, for someone who's new to the field, it's kind of scary to think of all these different models. But I guess you don't need to know that much to work in it, as I managed. OK, so for this talk, we're going to be talking about these terms: synchronous, asynchronous. Synchronous means that you assume all the processors send their messages in one time step, and then in the next time step, they all receive their messages. Asynchronous means that the adversary can arbitrarily delay or schedule the delivery of messages. And then there are things in between, which we're not going to worry about. In between would say that there's some time delay, but it's a fixed time delay, and everyone knows it in advance. In the general case, in the asynchronous case, the processors have no idea how long they have to wait to get a message. They can't afford to wait for all the messages, because it could be that there's some bad processor that they're waiting for, and he may never send. So you can't, they have no idea. There's no time limit. There's also a question of what kind of faults. Fail stop, Byzantine. Fail stop just means that the processor dies. Byzantine is really bad. It means that not only does the processor keep going when it's corrupted, but it sends out bad messages, messages designed to make you think the wrong thing, to make the good processors think the wrong thing. Sometimes they assume either a computationally bounded adversary, which means that if you have cryptography, there are cryptographic primitives such that the adversary can't be assumed to do the kind of computation needed to break the primitives. So you're safe. Cryptography works by assumption. Another possibility is that you have private channels, meaning that the adversary can't see what's passed between the processors. And the third possibility, and there's probably stuff in between, but a third possibility is called the full information model, which means that the adversary can see everything that's passed between processors. In the full information model, the only thing that can't be seen is the private random bits that a processor might toss a coin and see a private random bit that causes it to send something. So that the private random bits can't be seen ahead of time. Just the messages, and of course, the adversary knows the protocol. OK, and we're going to be working in the full information model. So we're going to assume no cryptography. OK? Now, there's different kinds of, there's something called a static and dynamic adversary, and that has meant different things. For the purpose of this talk, it's going to mean that the adversary has to pick, an adversary is static if it has to pick which processors are corrupted before it sees any of the randomness. In other words, at the start of the protocol, it has to decide which processors are going to be corrupt. OK, that's as opposed to a dynamic adversary, which can, somewhere later, as the program is running, it can pick which ones are corrupt. Now, if you're going to do leader election, pick one good processor to be the leader, you better have a static adversary, because otherwise the adversary will see who's going to be the leader, and once you know it, it picks that one to corrupt. OK, so you can't have leader election without some kind of assumption about a static adversary. OK, message passing. We're going to assume a message passing model, which means that each processor sends a message to one other processor. That means that the bad guy, a bad processor, while it might be expected to send the same, the protocol might call for a bad processor to send a message the same message to everybody. It can decide to send different messages to different processors, and nobody will know the difference. I mean, unless you can somehow figure out this. OK, so there are other things. There are in between. There are other notions of dynamic. Our adversary will be dynamic. It can react. It can decide what messages are going to be sent as the protocol is going. So it's not totally static. What it does is dependent on the messages that it sees as the protocol is being executed. The only thing that is static is the choice of the processes to corrupt. It's really weird. I can't hear myself talk, but you guys, I mean, it's like muffled, but it's clear. Great. Oh, great. This is some kind of bad thing for the speaker. It's a handicap, I guess. OK. Now, the other thing we're going to consider is whether the network is completely connected or whether it's a sparse network. And we're going to talk about both kinds of networks. We're actually going to show a result for a sparse network, meaning that each processor only has to talk to in our case, a polylog number of other processors. If there are n processors, a polylog in the number of processors. OK. Resiliency, I explained. We're going to time and bit complexity. You could ask how many bits of information need to be communicated. Now, believe it or not, we're going to be talking about randomized protocols, but people actually talk about quantum protocols now for Byzantine Agreement, but that's beyond us. We don't have to worry about that. And we're going to talk about these three problems, or really focusing on Byzantine Agreement, leader election, and from leader election, you also get global coin tossing. If you have a leader, that leader can toss a coin. So you have global coin tossing. All right, so for all you people who haven't seen this stuff before, like me, a couple of years ago, we'll start with an old protocol in 1983. It's designed to do asynchronous Byzantine Agreement. And it works like this. Essentially, every processor sends its bit to every other processor. If you have a large enough, if you see a large enough majority of one value versus another value, then you send that majority to the other processors. So you have a second round. So over here, there's like a second. I mean, it's asynchronous. The protocol is asynchronous, but you can put a number in your message to indicate that you're sort of in a second round. So if you get, after you've received enough messages from n minus t processors, then you sort of enter a second round where you send out the majority. If you've seen a large enough majority, you send out the majority value. OK, now you notice that you can never wait to hear from every processor, because you don't know what the adversary has done in terms of the schedule. It could be that the bad processors, the T bad processors, are not sending messages. So you can't wait for everyone to write back to you. You can, at most, you can wait for n minus t processors to write back to you. And when you do that, you don't know if you really got all the good processors or you're missing t good processors. The adversary could be fooling you. The bad guys could be writing back to you, and the good guys might be delayed. So you're always missing t responses. OK, then if you get a lot of these majorities, if you get enough of these majorities writing to you, so if you get enough of these second stage messages so that you know you're at least getting one from one good processor, then you set your bit to the value of that bit, the one that the majority picked. Finally, if you get enough of those majorities, then you're actually going to decide on that bit. And this thing keeps going and going. Oh, sorry. And if this doesn't occur, you flip a coin to determine your bit. And then it keeps going. And this protocol keeps executing. You keep executing and executing until you decide. That's what a processor does. OK, so there's a lot I want to tell you in this talk. So this is like a 1 minute, 1 second explanation of this protocol. I just want to give you a flavor for what was out there before our protocols. OK, so what happens in this protocol is that there's 2 points. There's a deciding point when enough people are in agreement, enough processors share the same bit. And then there's sort of a maintaining point when enough processors, when you sort of set your bit. If you hear from enough processors that they're in agreement, then you set your bit. If you hear from a lot of processors that they're in agreement, then you decide your bit. And in all these protocols, because of the way the adversary works, you always have you can't be sure if the protocol is in 2 states at the same time. Some processors are above this line, and some processors are below this line, because the adversary can arrange this by sending different things to different people. So what you can show in that protocol, the reason it works, is that if one processor decides to stick to a bit, it means that the next round, everybody's going to decide on the same bit. And the other thing that I want to say is that if you've set your bit, then there's some small probability that everybody, when they flip their coin, is going to pick the bit you set. So all the processors who end up flipping their coin might agree on the same bit. with probably like 1/2 to the whatever, however many there are, they might agree on the same bit. And that's when the protocol stops. Okay, so it takes that kind of exponentially low probability for all the processors to pick the same bit, and it happens to be the bit that some of the processors had previously set their bits to, for this protocol to decide. This protocol is an exponential time protocol. Okay? That was the only protocol they had for asynchronous Byzantine agreement in the full information model. Now, if the number of bad processors is square root n, then the protocol actually only takes constant time, because the bad guy can only the adversary can only introduce square root n deviation. So it's likely that you're going to have a majority which is off by which is maybe a majority by square root n. So it doesn't matter what the adversary does. So if there are very few bad corrupted processors, this thing will work pretty quickly. All right. Now, in 1985, Braca, by the way, improved Benor's algorithm by increasing the resiliency. He also came up with a way to make the whole thing much faster, like log n time. And what he did is he grouped the processors in these, what he called committees. And they were small. The only problem, so they were small and they're very few, and the way he designed it, he used a method of designing, actually it was a random method of picking these committees, so that almost all of them would contain a majority of good processors. And only a couple of them would be bad. So he sort of ran it from a higher level. Each of these would produce a bit, and there'd only be like square root n bad guys. Square root of the number of these committees would be bad. So now he reduced it to the case where you only have square root n faulty bits, bits that were faulty, that the adversary would control, so that then it would take constant time from there. So each of these would produce a bit, and then with only a small number of faulty ones, in the next another constant number of rounds, and they'd come to agreement. The problem is that in order to do this, the bits that these produced had to be secret. The adversary couldn't know what the bits were. Okay, so this introduced the notion of using cryptography or private channels to do this problem quickly. Yeah?
You say the bits that each committee produces or each processor?
Well, the bits that each committee, the messages had to be secret. The messages that they sent to each other had to be secret. Okay, so this is what I said. So square root n of the total committees were good, and then it would only take all one time to bring it to agreement. An alternative perspective was Rabin, who assumed that there was the existence of a global coin toss. If you could assume the existence of a global coin toss, then you could sort of randomly pick a threshold when you come to agreement, and that defeats the adversary, because the adversary could play around a threshold, could assign bits so that they're around a threshold. But if you could randomly choose your threshold, and the adversary didn't know what those random bits were in advance, that would defeat the adversary. But that assumed the existence of a global coin flip, which, in other words, that everybody would agree on the same random bit, and that there's no way that's an additional assumption from the model. Okay, so after this, there were two directions that the research took. One direction was we're going to continue in the message passing model, but we're going to either assume private channels or we're going to use cryptographic protocols. And we're going to assume that the adversary can't break these cryptographic protocols. Namely, it can't do more than polynomial time computation, something like this. And they were able to get an O of 1 expected time protocol using n-squared messages of communication. Now, on the other hand, there were people who said, OK, let's just assume we have atomic broadcasts. So in fact, we assume away the Byzantine Agreement problem altogether. We assume that every processor, when it writes, it has to send the same thing to everybody. So the bad processor can't tell some people something and some people another. And when you have this, Byzantine agreement is simple. I mean, everybody just comes to agreement. But let's try some harder problems. Let's see if we can do leader election. Let's see if we could do global coin toss in that kind of context. So the other thing that they assumed is that the adversary was non-adaptive in the sense that I described earlier. That is, it had to pick the bad processors at the very beginning. And now let's see if we could do leader election. OK, so these two went off. This stuff was around 2000. This stuff actually ended up, I guess, around 2000 or so, people came up with these, or earlier, people came up with these protocols. OK, so for leader election, the best is a tight upper and lower bound. The best is log star n with these atomic broadcasts. And that gives you a constant probability of success. OK, now I just want to say one thing. I discovered this lower bound that wasn't so widely known. If you have a randomized protocol to do Byzantine agreement, even if you have private channels, even if you have a non-adaptive adversary, even if your adversary can't even use the messages that are being sent, can't do anything, doesn't know anything, has to decide its strategy ahead of time. Even if you have cryptography, you always get a probability of failure, which is at least this, the number of rounds raised to the number of rounds, even in a synchronous protocol. OK, so if you have a synchronous protocol, you have everything you want, you get this probability of failure. So for example, you're going to have a probability of failure of 1 over n, bigger than 1 over n, if you have less than log n over log n rounds. And that applies to all the cryptographic protocols, any of the protocols. OK, so they have expected time of 1, these cryptographic protocols. But if you're looking at the probability of failure, it can get significant. And it's given by this. So in other words, it's a constant if you only have a constant number of rounds. All right. So I hope you're all on, because I have a lot to tell you. So this is a very neat method. If you don't remember, this will be the thing you take away from this talk. And it's not mine, but it's very neat. OK? This is Feige's method. It's for picking doing leader election in the broadcast model. OK, so maybe this would be a good question for asking people when you interview them or something. You have this notorious method of interviewing people. So, OK, suppose you have a set of processors, and you want to elect a subcommittee. How can you do this if the adversary can listen to what everybody says before the bad processors can listen to what everybody says before they say anything? So like you're in the playground, and you say, who wants to be on this team? And the adversary, the bad guys, can wait until all the good kids talk, and then the bad kids can then raise their hand and say whatever they want to say after they heard the good kids talk. OK, that's what's going on. What kind of protocol could you design? Well, here is a really simple protocol. Everybody picks a random number from 1 to the number of bins. You have to pick 1 to k. Now, you pick the group. So you have k buckets. You look at the bucket which the fewest people have picked. And that becomes your subcommittee. OK, now, that's it. That's the protocol. Why is this so good? The good guys will randomly pick a bucket. The bad guys, well, they'll do whatever they can to get into the lightest bucket. But what can they do? How many bad guys will fit into the lightest bucket? If they all pick the lightest bucket, it won't be the lightest bucket anymore. So what happens is the good guys spread themselves out relatively evenly, and the bad guys can't put too many in the lightest bucket, or it won't be the lightest bucket anymore. So you maybe get a few more bad guys than you would have had in the general population, but it will still be relatively balanced and similar in proportion to the fraction that you find in the whole population. OK, so that's Feige's lightest bin protocol. If you repeat this over and over again, you can eventually get down to 1 guy. And that's your leader. And with some constant probability, that leader is a good processor. OK, so that's pretty much the protocol, his protocol. OK, and we're going to be using that protocol. All right. So in our work, what we're going to do is we're going to stay in the full information model, non-adaptive, okay? We're going to have to assume that the adversary picks the bad guys at the start. We're going to solve these problems, and, however, we're going to use the message passing model. We're not going to assume atomic broadcast, and we're going to show how we can do Byzantine agreement. Okay, what we were aiming for in our research is to get something that doesn't use too many messages. We wanted to get below n squared messages. We wanted to use polylog messages, polylog bits per processor of communication. And so that we called scalable. Maybe a misuse of the word, but scalable meant that each processor was only sending out a polylog number of bits. And we wanted this to take polylog time, not exponential time, but polylog time. Okay, so a huge drop in the amount of time. In the full information model, no cryptography, everything is known to the adversary. Okay, so what was previously known? Well, in the desynchronous model, there was an O of n time, n rounds. There was t over log n, so if n was n over 3, so it's n over log n. In the asynchronous model, nothing was better than the one I just showed you, exponential time. All right, now the way our protocol works is simple. Our goal is to get a small set, a committee, just to get a small set of processors that are representative of the whole population, that contain we want all the processors to agree on a small representative set of processors. That is, a set of processors which contain a substantial number of good processors. Okay, so how can we get all the processors to agree on this small set? That's our goal. Once we have a small set, this representative set, they can run Byzantine agreement, they can run leader election, they can run whatever they want to run. Because they're so small, it doesn't take them very much time. Even if they use the exponential time algorithm, if they're log n, whatever, they're small enough so that they can spend that time getting the result. So the main goal then is to get the number of processors down to a small representative set. Okay? So specific results that we had, we found synchronous scalable protocol, which constructs polylog-sized committees with some probability. And then, therefore, we can do Byzantine agreement and leader election. And the only thing is that we didn't quite have Byzantine agreement. We got the committee. We were able to get a small committee. But we couldn't get everybody agreeing to it. We had to leave out a small fraction of processors who didn't know this committee. Namely, about 1 over log n of the good fraction of good processors were left out of the process. So there's a term for that. It was called almost everywhere agreement. We got almost everywhere agreement. And we got that on a sparse network as well. Now, if we allow a broadcast, if we allowed everybody to send bits to everybody, we would get complete agreement. We just needed to tell everybody about it, and then everybody would be in complete agreement. But if we restricted ourselves to only polylog number of messages, we couldn't get beyond the almost everywhere agreement. And that remains an open problem. We don't know if restricting the communication to polylog number of bits per processor means that you can't get everywhere Byzantine agreement. That's an open problem. It's a fundamental open problem in Byzantine agreement. No one has ever done Byzantine agreement everywhere with less than n squared bits. Okay, so we got this on a sparse network as well. Not just any sparse network. We designed the sparse network. And we were able to recently get it for the asynchronous model, okay? And probably the asynchronous model is scalable. We just never bothered to check that out. Probably I would guess that you can take our protocol and make it scalable as well. So not too many bits, but then you leave out a small fraction of processors. And there's also a lower bound, but I won't go into this. It's not a great lower bound. It's not what we would have wanted. OK, so let me just go to how this protocol works. Okay, so the idea is that you reduce the number of eligible processors until you end up with a small representative group at the top. Okay? So there's different stages where you gradually reduce the number of number of potential members of this committee, and it gets smaller and smaller. Okay, so key to what we're doing is the notion of an extractor, which is also called an averaging sampler, which is also called a disperser. So it's this combinatorial object which has many names and is used for many things. And it started, I guess they were invented in order to do, they were invented, partly Braca invented them for distributed computing, and they were also invented to use randomness extraction. Okay, so what's an extractor? It's a bipartite graph. And you can construct one by constructing a random bipartite graph, and there's also deterministic methods of constructing these things. Okay, and it has the property that if you have any subset of bad processors, red processors, then almost every node on the top, if you look at the set that's determined by their neighbors, the fraction of red processors in it, in their neighbor set, is similar to the fraction in the whole population. So in other words, you get a bunch of subsets which are sort of representative of the whole population, except sometimes you get some bad subsets. Okay, so this just happens. If you take a random bipartite graph, this will happen. You'll get this kind of thing. Okay, so you have a little fudge factor. You don't quite have the same fraction of bad processors. You might have a little bit more. All right, so now filling in what our protocol is going to look like. Sorry, this is, I actually used to do all my slides by hand. So this was like the first slide. I did this about, I don't know, half a year ago or something. And it was kind of messy because I'm not very good at this. I'm getting better, though. By the end of the talk, the slides get better. Anyhow, here you see an extractor. And then what will happen, so these will be the initial processors. They'll be formed into committees. Each of these committees will elect a subcommittee using the FIGA, essentially using the FIGA protocol. That will then they'll output the processors in the subcommittee. The number of processors on this level will be reduced by a factor of log n. And then the process continues until eventually at the very top you have a small committee. Okay, so for the remainder of the talk, I'm going to talk about what it takes to do this in an asynchronous environment. And I'm also going to talk about how you can do it on a sparse network. Okay, so we're going to use, as I said, we're going to use FIGA's subcommittee election protocol to elect a subcommittee. But that was in a broadcast model. This is in an asynchronous message passing model. Okay, so if you remember, this is the picture of FIGA's algorithm, right? Every processor picks a bin, and you pick the processors in the lightest bin. All right, but there's serious problems to contend with. Problem one. First of all, we don't have the broadcast model anymore. We have message passing. So you have to wait to hear from processors. But you may hear from one set of processors. Someone else might hear from a different. Remember, the adversary can delay messages. So, and you can't wait. Because it's asynchronous, you can't wait to hear from everybody. So somebody will hear from one subset of processors, somebody will hear from a different subset of processors, and you all have to agree. So you have to run Byzantine Agreement within this to figure out who you're actually hearing from and what they sent. Problem two. you could have, the adversary could be really mean. He could prevent, or she, or it, could prevent someone from hearing from all the processors from hearing from some processor. You may never find out the choice of some processors. So in that case, I mean, eventually you will, but you can't afford to wait. You don't know how long you have to wait. You can't afford to wait for everybody. So you have to kind of content yourself with actually not knowing everyone's choices. You might just, everybody might just agree that this processor's choice is star, undetermined. Okay. So in fact, what we did is we said, okay, let's say you don't hear from most of the processors. Still, we can show that you will hear from some constant fraction of processors. So we're not going to know everyone's bin choices. We're not going to know most processors' bin choices. But we are going to agree on some constant fraction of the processor's bin choices. And here, this seems to be the worst possible problem. Why doesn't the adversary just decide, OK, I'm going to put my processors in bin 1. And anyone who chose bin 1, I'm going to delay. OK, what happens then? Well, everyone has to come to a decision. They don't see any good processors picking bin 1. Now, bin 1, the adversary arranges it so that just the right amount go into bin 1 so that that becomes the lightest bin. And your subcommittee contains all bad processors. OK, you see that's a problem, right? If you're awake, if you're following my talk, which doesn't sound comprehensible from this angle. So the adversary can arrange that only bad processors are in the lightest bin, just by delaying all the other guys. So we have a fix to this problem. And I think it's interesting. And I'm trying to see, I think it has a general application, but I haven't quite figured out what that general application is. OK. So what we're going to do, if there are k processors, so the idea is to prevent the adversary from using delay to selectively, from picking, from being able to pick to delay processors based on their bin choice. OK, now it can hear all the messages. So how can we prevent this? Okay, so here's what we're going to do. We're going to, let's say there are k processors. We're going to run the bin selection protocol k times. And every time that, in round I, each processor is not only going to say what their choice is for round I, but it's going to say what their choice is for round I minus 1, I minus 2, back to the start. So if it ever gets heard, all the processors that hear it are going to learn its choices for all the previous rounds. OK. Now I claim that there must be some round j such that the entire set of processors whose choices were known for that round their choices are also going to be known for the following round. And those choices are going to be random. OK, now I kind of have to explain why this is true. All right, so here's a table. So imagine that each processor is listening to all the messages, and it's kind of putting together this table. And it's saying, OK, in the first round, I didn't hear from this processor. I didn't hear from this processor. And assume it's Byzantine Agreement, so we all hear the same thing. This processor didn't. We don't have a message for this one. We don't have a message for this one. But we heard this one pick bin 3, and we heard this one pick bin 2. OK, and maybe a couple more rounds go by. I still didn't hear from this, but I know this guy, I now know these, and so on. So if you notice, the set of these, if there's a star, it has to be in the top. It has to be starred from then on, right? So the the set of stars has to be increasing. If you have k rounds, the set of stars can only increase k times. So if you have, well, k plus 1 rounds, say if you're starting from nothing, then you're going to have one that's repeated. You're going to have a row. You're going to have a row where the set of stars remains unchanged. Okay, that's the one we pick. We pick the second time that you have a row where the set of stars remains unchanged. Why do we pick that one? There has to be such a one, and although the adversary can force us to pick one, these have to be are somewhat independent. If this set is fixed, the adversary picked this. These can't be, these are somewhat random. So they're random subject to the adversary deciding which row he's going to pick. Okay, so on this level, these bin choices are going to spread out. So the adversary can't decide that it's going to star all the ones that pick one. Because if it did that, it would have to star this one. But if it starred this one, then this would not be the row we'd pick, because the star would have to be here too. Okay, so we've restricted what the adversary can pick. We've kind of defeated the adversary from deciding who to delay based on the content of the message. Yeah?
How many rounds do you have to wait until you get a stable?
If there are because if the rounds are not stable, then the number of stars are increasing. It's a monotone function. So you're going to have stability equal to at least, the number of there's only k columns. If the number of columns with stars is increasing, then after k time, it's got to stabilize. Now, k in this case is could be as little as log n. It depends on how big these committees are. Okay, so k is not large. K is just the set of the size of the committee, or log n, depending on log n. Yeah?
Just to make sure I understand this, so an adversary can fix it such that for any given row, choosing that row would make it such that he would overflow the lightest bit. However, he can't force you to choose that row. So is that the idea? So that says that the top row is a bad row. He can't force you to make it, to choose it, because he can't have control of the rows before.
Well, actually, no. The adversary can force you to pick a row. All he has to do, the adversary can force you to pick a row. All he has to do is delay the same set of processors. If the first time he delays the same set of processors, you're forced to pick that row.
Then that's a good row.
Yes, then that's a good row, because he can't have picked those stars by what the message was. Okay. Now, to fix the second problem, so we fixed the third problem, which seemed to be the worst problem. The second problem said that we really don't know a lot of bin choices by a lot of processors. So it could be that we actually have more bad processors than good processors whose choices we know. Still, if we only have a small number of good processors, we're able to use extractors to take a small amount of randomness to pick something that's good. We turn the extractor on its side, and I figured out how to rotate the image, so I didn't have to write it again, but it's still as sloppy as it was last time. And now we use the random bits that are generated by the processors in the lightest bin. Most of those bits are bad. Most of those bits were generated by bad processors. However, there's a small number of those bits, a small constant fraction, which were generated by good processors, which means that's enough entropy so that if I use those bits to pick one of these sets, since so many of them are good, it's enough entropy to pick a good one. It will likely pick a good one, which means that it will pick a subset of the original committee which has the right proportion of good processors. So even though in the bin I didn't have the right proportion, I can reestablish the right proportion. OK. Oops. That's it. I just put it all together in that tower. And I mean, it's not it. There's one more complication, which is that because it's asynchronous, every processor does not have the same view of what's going on as every other processor, because it's getting different messages. But we can show that it has enough of the same view, that they will agree on enough of the same processors in the top committee, that a majority will be good, and they'll all get the same. And if all those good processors agree, they'll all get the same information from those good processors. All right, and to speed this up, we had a recurse. So remember I told you that within the FIGA committee protocol, we had to run Byzantine Agreement in order to get agreement as to what the values of the bin choices were. So we recursively use our protocol to do that to speed it up. However, this causes the probability of success to go down. All right, so that concludes part one, and I'm sure I'm talking a long time. How am I, is anybody anxious to run? I don't know how, I have like 9 minutes or something. Or when did I start? I don't know. Is that all right? I'll talk for another few minutes. You can chase me off. Maybe I have a hook or something. OK, what happens in a sparse network? Now, we don't want to send messages to everybody. We want to be, we just want to send polylog number of messages to each processor. So this has never been done before. And so we want to do this. What can we do? The problem is that when you get elected up there, and someone else gets elected up here, they don't know. They have to know who each other is to do this election protocol, right? They have to exchange bin numbers. But they have to know who they are, right? OK, so all right. So what we do is, believe it or not, this is the same diagram you saw, but it's implemented differently. So for each node that I showed you, remember those BRCA committee nodes? They're replaced by sets of processors. And the sets are getting bigger and bigger. So you construct an overlay network where you start off at the bottom, and now to run an election up on some level, you send messages up through the network and back down to the processors that are involved in the same election. Okay, so if you are involved in the same committee election, you have to communicate through a sparse network by sending messages up and then back down. OK, all right. So in a single election, you'll have to send messages up and back through the node that represents the election. This gets a little complicated, and I don't really have time for the details. The problem is that there's a denial of service attack possible. We consider the possibility that the adversary will swamp a processor with a lot of requests or a lot of messages, and the processor has to know which one to relay and which one not. And since it can only send polylog number of bits, it has to make a decision. So we have to deal with that problem, how to deal with this denial of service. And the way we deal with it is we construct a protocol so that you know exactly who should be sending to you. So you only relay the messages of the people who should be sending to you. And OK. So OK, let me just switch to open problems and conclusions. OK. There's a lot of open problems, and every day I think of more of them. OK, so first of all, we don't know for an adaptive adversary, if you could corrupt processors on the fly, there's nothing better than exponential time in the asynchronous model. But we do know you can't do better than square root n. There's a lower bound, even for synchronous protocols. We don't know if it's possible to do Byzantine agreement, even with cryptography, even with private channels, in less than O of n squared messages. The rest, as I mentioned, I think there might be some general technique for simulating synchronous with asynchronous, but I haven't quite figured it out. And I also think that the idea of picking agreeing on a representative sample might have some interesting applications, but I don't know what they are. An interesting thing about the full information model is that you don't need the same kind of randomness that you need to do cryptography. It's been proved that in order to do cryptography, certain functions in cryptography, you need to have perfect randomness. And you don't need that for this kind of thing. You can actually take less random sources and pool them together to get randomness in this model. OK. And finally, I just want to tell you that the theory conference, STOCK, 08 is going to be in Victoria on Vancouver Island in the spring. I'm one of the local hosts. I hope you all come. I'd be happy to see you there. And it's really beautiful. And we're all going to stay at this hotel, unless you want to bail out and stay at a cheap hotel. But that's the conference hotel. So I hope you'll come. And finally, one last thing. Thank you. Any questions?